Recording is rolling. It is Monday, May 13th. That's 4 days until the exam. All right, so I'm gonna continue doing challenge questions, playing off these posters, pick up where we left off last week. All right, so for school context, we're on this fun schedule today. All right, so sixth period has 2.5 hours. I'm gonna try to at least make the most of this. And then also for context, today right now is going on the AP calculus exam. So a little over half the class is out. That's all right. We're gonna keep going on with this, and anybody's taking calculus wants to see what we did, they can find this video. All right, so here we go. Some posters. You guys remember last week we were doing posters. That's when we got some challenge questions. All right, I'll show you guys. I made some new posters over the weekend. So let me show you these two guys. All right, now this one we had gone over last week. So yeah, this would be a good poster. So this poster, right? Really good chance you're going to get this question. Actually, this question down this green box. They're probably going to ask you, right? So you have a planet that's so many times Earth's mass and so many times Earth's radius. You have sometimes the mass and 3 times the radius. These are the exact numbers I used last week, for example. Right? They're probably not going to ask you density, but that's how you can solve density. Right? Ratio densities, right? Mass per unit volume. Volume is proportional to radius cubed. Right? The 4/3 pi ends up canceling that in matter. Right? So we got sometimes the mass. Right? Remember, 3 times the radius, but turn that to volume, it's a cubic relationship. 3 cubed is 27. That's where that comes from. Right? Everything else cancels out. Right? Yeah. Right. So okay. So that's what's that? Approximately a quarter of the density of Earth dirt. Right. Whatever Earth dirt is, a quarter of that. So I have a giant styrofoam pup man. Right. And you're not going to get that question, but really good chance you're going to get this green question. Right. So what's the gravity field of the surface? Okay. So, guys, your gravity field here. Guys, write on your paper. What is the, in terms of variables and universal gravity constant, what's the formula for a gravity field? G equals, here, it's a fraction. Okay, that's what I'm looking for. Gravity field surface of a planet. In terms of universal gravity constant, the mass of the planet, the radius of the planet. Okay, can you guys get that? Okay. I'm looking for a gravity field at the surface of any planet. As long as you know the mass of the planet and its radial size. I'm looking for in terms of variables. Okay, who's going to get this? All right, that's orbital speed. Okay. Yeah, GM over R squared. There you go. All right. Right. So universal gravity constant times the mass of the planet divided by radial size of the planet squared. Right? Here, all right, let's walk around. Guess we're struggling on that a little bit more than I thought. So here's some related formulas. If you go gravity force, as in your weight, could that be GMM over R squared? That could be that, right? So orbital speed out there, you could set this gravity force equal to centripetal force, and then at the end of that, you get the orbital for a circular orbit is square root GM on R, right? How'd you guys derive that? You guys remember that? Right. Okay, so a little bit. All right, so I'm going to start with this one right here and say, here, guys. Universal gravity constant, mass of Earth, radius of Earth squared. Right, that goes boink right there. And then this new planet X. All right, well, I just scaled up mass by some times and radius by some times. But don't forget the radius gets squared. And then everything just cancels out. Universal gravity constant cancels out, blah, blah, blah. Right. So 7 over 3 squared is what it's be. Okay. Right. So guys, when you see that question 4 days from now, you're gonna get that one right, right? Right. You guys got that in your notes. All right. What else got here? Ooh, all right, here's another one you guys saw recently. I'll turn this into a poster too. Right. Guys, you know you're gonna see something on this one, right? Here, I have 16 questions lined up right here, 8 and 8. Right? If you see a Ferris wheel, this is maybe a rigid circle, constant angular velocity. Now this is vertically oriented. A ball and string, this one I've also got vertically oriented, just so I can do closer comparison as I can do, right? The 3-by diagrams were kind of a little bit different, right? So here, Ferris wheel, notice the weights are all the same, right? And the normal force changes, right? Now, if you're swinging through the bottom, there has to be an overall net force up. Actually, this exact question, this one right here, is a question you guys saw on a recent FRQ. You guys remember that? Right? But you could be asked any of this, right? Say going around the top, look maybe more like that. Right? Notice going around the sides, there should be some small inward acting force to act out to provide the centrifugal force, right? Maybe it's a friction force to prevent, say, a book sliding around or something, right? Right. Now, a ball on a string is going to be different. Notice that the weight's the same all the way around, right? It's always the same weight. kind of, right? But ooh, the tension force. Right? You guys see, that's always directed straight towards the center of the circle, right? No, that's not the net force, right? The combination of these two would be net force, right? So the speed of the ball is changing all the way around, right? So it's speeding up on the way down, slowing down on the way up, right? Unless they specify otherwise, which they could, but that would be a weird situation, right? The way I did it is maybe something closer to constant mechanical energy for the Earth ball system, which would be a lot more realistic. Okay. All right. So you guys ready to field any question off that poster there? Right there. There's 16 questions they can ask right there. All right. Okay, you guys got those? All right. What's next? Oh yeah, this one. Kinetic energy derivation. Right, so are they gonna ask us is this exactly? Probably not, but here's but the skill you're definitely gonna have, right? Where you substitute different formulas. So yeah, let's go through this just to have the general skill, right? Suppose you start with work energy theorem. I mean, you're gonna get work energy theorem. That's gonna happen, right? Say you push on a asteroid with some force from some distance, or what if a rocket blasts its engines with some blast force for some distance, right? Okay, so be going to energy. By the way, if they say a rocket blasts its engines with some force for some time, that's not an energy question. That would be a what question. Force times time is not energy. It's what? Impulse momentum, right? Right. Okay. The force times distance, that's like energy and work, right? Right. So the reason I'm saying something out in deep space is just to not worry about any gravitational potential energy or height changes, right? Right. So it would all go into kinetic energy at that point, right? Rocket in deep space or push on asteroid. Right. Oh, I know F equals ma, and then I know from kinematic days. Ooh, where's my well, okay, you guys wrote the 3 kinematic formulas. I got got them right here. For my here they are. Right. Oh, right. So take one of these, rearrange it. I can solve for acceleration and substitute it. And it looks like I picked this very last one. This very last one. I solve for that A. Right. Oh yeah. Right. I've also kind of assumed here that I'm starting from rest. Right. We'll simplify. Right. You get 1/2 of me squared. Right. So yeah, the skill that you want to have ready to go, right, you're going to have to apply is, can you substitute some expressions into other expressions to get some end result? Okay. Okay. Ooh, right. Here's a poster I've needed to be making for a long time. You guys remember acceleration is this bridge variable? Hey, look, it's a bridge. Ooh, between kinematic and dynamics. You guys remember that? Right. So dynamics, it's just Newton's second law of motion. Right. This right here, this is Newton's second law of motion. Hey, you guys see this? Right. And then the kinematic side, well, there's those 3 kinematic formulas. Now I can rearrange them to solve for A. You guys see, it's really the 3 kinematic formulas just in terms of acceleration. Right? Acceleration is equal to first, second, third. All right. Okay, okay. There you go. All right. So if you have to bridge back and forth, let's say, right, you kick a ball with some force, right? The ball has some mass, kick with some force, and then for some time, like how fast is it going? Okay. Right. So it'd be bridging from here to here. And then here's the rotational version of this. Right, so you got angular acceleration. This could be a turntable speeding up spinning. Maybe, right? If you apply a torque on some rotational inertia. Right. And here's the rotational kinematic. Okay. All right, guys, got all that? All right. Bridge variables there. I'm gonna say there's a 50-50 chance you're gonna get this question. This question. AP likes this question. Right? And you guys have seen this question, I think, a few times before, right? Does this look familiar, hopefully? Right? What if you have a disk with some rotational inertia and you drop it down onto an already spinning disk? That's usually how AP likes to ask that question. I've seen it a few times before. I think you guys have seen this a few times before. Right? Let's say there's some friction between those 2 surfaces. Right? So say, do you guys think that when this stationary blue disk drops on top of this rotating red disk, that they're going to rotate together because of this friction, right? You think the blue disk is going to, well, definitely speed up because it wasn't moving before. Now it's going to start spinning, right? And this red disk is going to kind of slow down a bit, right? But what about angular momentum of the entire system? What does that do? Stay the same. That's conserved. Right. This is a unit 7 question type, isn't it? Yeah. Right. So here's for the 2-disk system, stays the same, right? And then here's the drop time. So there's this time I'm dropping it, right? Short period where they're like catching up, right? Right. So there we go. So the blue disk wasn't spinning at all, right? Now it is I times omega, right? And the red disk, slowed down a bit. Right? Now these numbers play out. I have the red disk maybe like twice as thick as the blue disk, so it has twice the rotational inertia, things like that. Okay. Guys, yeah. All right. This one could be handy. This is a little extra, right? If you feel really comfortable with this class, you want to do a little extra stuff. Yeah, this could possibly help you out. Relationship between kinetic energy and momentum. I've got a proof over here, a derivation, and then here's the end result for linear, and here's the end result for rotational. Boom, boom. Right. This could be good to know. I've seen some recent FRQs that we did in class where that came up as a possible answer that could get you points, right? Although usually with something like this, there's other ways you could also answer the question, right? That this could possibly pick up on. And do I have what? Oh, okay. Those ones just for my honor students. Maxwell's Demon, but yeah, if that looks interesting, you can look at that. All right, there you go. There's the extra posters I just made over the weekend. All right, now let's go kind of back in order. So far in this class, last week we hit unit 1, 2, and 3. That was kinematic motion, dynamics, and then unit 3 is like circular and gravitational orbits. So we're moving on to unit 4, which is energy and work. Right? Energy and work. Right? So here we go. Right, you guys got your notes out, right? Or just gave you some paper, one or the other. You have notebooks and papers. Guys, write down what is the formula for work. Work equals what expression am I covering up right here? Force times distance. Boom. Oh, here, show you guys that much anyway. Okay. Potential energy. Now I have two versions of this. Really, you're only going to need one of them for this exam. Guys, what's the one that you care about for this exam? MGH, right? Right. You guys know you're going to use that, right? MGH, right? So mass times gravity times height change, right? If I take this object, I lift it up like 1 meter, up 1 meter, you go h, sit on it, right? Right. Now there's a more universal form because that lowercase g is, well, you know, changing. If that height is changes small compared to the radius of the planet, right? So what if it's not? What if you're blasting a rocket to the moon? You can use this form, right? It's a little trickier. You might see this one in college, maybe, right? But right. Use it for escape speed or something. All right, next one. Spring potential energy. What's the formula for that? 1/2 kx squared. There you go. Right. A lot of students tend to mix this up with Hooke's law. F equals kx. Energy is 1/2 kx squared. Okay, but you guys got that. Right. And then kinetic energy. What's the formula for that? 1/2 mv squared. Oh, I just showed you guys the derivation of that from work energy theorem and kinematic. Exactly. 1/2 I omega squared. Boom, 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 boom. You guys got all those? All right. What's next here? Oh, variables and okay. All right. So there you go. Okay. So these are all in joules, powers, and guys, what does this W stand for in this context as a unit? Powers measured in watts. Guys, what is 1 watt? Is that 1 joule per second? Right? Right. Like energy per time, work per time, right? I threw in momentum here. We're not quite at yet, but we're going to get to, right? Kilogram meter per second. Impulse is a change of momentum, which is usually written as Newton seconds because force times time, right? But these two units are actually equivalent, aren't they? Right? Right. Because the Newton breaks down to kilogram meter per second squared. All right. Right. Energy measured in joules. Right. 1 joule breaks down to 1 Newton times 1 meter, which further breaks down to kilogram meter squared per second squared. Okay. And if you somehow forgot that or drew a blank, you guys just told me a minute ago, work equals force times distance. Oh, so work could be some energy transfer in joules. Here's force in newtons, here's distance in meters. Boom, boom, boom. It's all there, right? The units line up with the variables, right? And power, 1 watt, you guys just told me a minute ago, right? That's 1 joule per second, which breaks down to these fundamental units. Okay. Boom, boom, boom. You guys got this? All right, what's next? Ooh, well, here, I'll show you this one. Work equals force times distance. Now it's really a dot product. So if you got some force and some distance movement that are different angles to each other, then you have to multiply by the cosine of the angle between those, right? Now careful, because sometimes the problem likes to give you a different angle. Like guys, what if you were given, instead of this blue theta up here, what if you were given this angle down here? Then you could say the work done lifting this object up this staircase would be, yes, I'm lifting with some force. And yes, I moved up this diagonal distance. But would it be sine or cosine of this angle? Yeah, it'd be sine of this angle, wouldn't it? So careful, watch for that. Right? So you need the components that are parallel to each other. Right? That's the key. Right? If the angle really is between them, as I put it on this poster, then it is cosine. Okay. Right. Right. Ooh, guys, you're gonna see that graph, right? Right. force versus distance set of axes. Oh yeah. Oh, okay, yeah. All right. All right. All right. So you guys know you're going to see force times distance. Application of this might possibly be work energy theorem, right? If you push on something for some distance, say like how much does it speed up, right? It might be a conservation of energy type application, right? This could be the first part of it. Right? Next here, closed and open systems. Right, so here's conservation of energy. Right? But if the system is open, now there are different perspectives on how to define an open system, right? Here's the energy perspective, is that there's work being either done on or by the system, right? That's the plus or minus, right? There's energy that's leaving or entering the system, right? So, right? The force perspective on open system is that there could be an external force. That just goes hand in hand, right? Force and resistance, something like that. If that comes up as a free response question, you have to write that out on paragraph form. They should accept either of those explanations for what makes something open or closed, right? Either there could be work done on or by the system, or there could be an external force. This next one. Okay. Right, this next one, let's do this. Okay. Galileo drops the ball from Leaning Tower. What's the crash speed? Go ahead and drive that whole thing right there. Drive that one from scratch. Aha, all right. It's got to be a winner. All right, Catherine's winner. All right, got a couple of winners. All right, so if this was a free response question, that's the first line I would write right there. Right, I would indicate to the AP grader, yep, I know it's a conservation of energy question, or well, this is one way to solve it. Okay. And then, okay, potential energy at the top, kinetic energy at the bottom, right? 100% that, 100% that, top, bottom. And then, okay, the mass of the object cancels out, and the speed at the bottom is square root 2gh. Boom. Okay. Because what if instead of dropping the ball, what if you threw the ball straight down? Right? Could you do here? Let me give you guys multiple choice. What if you throw the ball? So, right, throw ball downward. I guess that need not be downward necessarily, just throwing it in general. Right? So, is it? I'll give you guys multiple choice, either A or B. Is it V final equals V initial plus square root 2gh, or is it the square root of V initial squared plus 2gh? How would that play out? Is it A or B? Let me see. Show hands. Show hands. Who remembers this? Who thinks the answer is A? Who thinks the answer is B? Yeah. Right. So and you can show that either with conservation of energy or with kinematic. Right. Either way, you'll get option B. Yeah. So A and B. Bing. That's it right there. All right. So you guys get there. All right. Yes. Speaking of which, here's the other way you could have gone. Right. So you got kinematic and energy methods. Right. Hey, what if you want to throw the ball straight up? Now, this is a really similar problem. It's kind of the same problem in reverse in a way, right? It's like how high does the ball go as a function of how fast did you throw it, right? You could also ask a similar question: what speed did you throw it, given how high does it go, right? Which, if you look at that format, it's just like the previous poster, right? That v square root 2gh. It's just like that too, right? Doesn't it? Okay. Yeah, so you can go kinematic or you can go energy. Right, guys build that. All right. Let's see what's next. This one. Okay. I'm curious to see who's gonna craft the correct equation for this. Okay. Say I got this mass pushed against that spring, compressed it some distance x, let it go. Fly around this loop. Say there's no friction on the track, don't worry about that. Right? And I want to know what is the speed of this object at the top of the loop. Right? Now, I didn't solve out that whole problem on this poster, but I wanted to see if you guys can do the correct conservation of energy setup. Let's see if you can do it. Right, walk around so you can do this correctly. Just do the setup. How do you set that up? Conservation of energy. Yeah, all right, Alec got it. Oh, that's it. That's all. Yeah. Um, yeah. Although, yeah, if you were going to figure out what is the speed, then you solve that speed. You know, give it, but they'd have to give you some numbers for everything else, or assumptions for something. All right, Connor got it. Catherine got it. All right, got 3 winners. 3 winners. All right, so there you go. Like I said, when the object was pushed against the spring, that's all 1/kx squared. Right? That was the source of energy. Right? By the time it gets to this point in the loop, well, the energy's gone 2 places. Had to lift this height, right? So that's mgh, potential energy that way, right? And whatever was left over is now in kinetic energy, 1/2 squared. Right? Right. Now, if they gave you some numbers, then you could solve for an exact speed, right? If you knew what was the mass of the object, what's the height. What AP1 likes to do too is ask conceptual like scaling type questions, which would be kind of tricky for this. But here, how about this? What if you had a light mass versus heavy mass? What if you push this against the spring versus this against the spring? Right. Guys, which one of these is going to be going faster at the top? Yeah, a little tiny one, right? No, no one's. Yeah. There we go. Ooh. Let's do outward energy. Right? So, actually, I think you guys saw this question recently. This looks familiar, right? So we got an outward set up. There's a bunch of questions that get asked about the outward. The most obvious question is, what's the downward acceleration of the large mass, right? They could also ask something about the tension in the string, right? And a question that came up on a recent FRQ that we did was, after moving some height change, some distance, right? This one's going down, this one's going up, right? What is the speed at the end of that? And I remember there were actually 2 different approaches you could do. One approach is you could do the full dynamics, figure out the acceleration, and then flip back over to kinematic motion and say, well, now they know the acceleration, if it starts from rest, they can figure out how fast it's going after some distance with that third kinematic equation. Okay? But there's a faster way to solve it, and that's using conservation of energy. So can you set up the correct conservation of energy for this? Oh, here, give me that much energy. It's called the M1, M2 Earth system, in which case energy would be conserved. So that pulley is ideal pulley, no frictional losses. All right, so what does the conservation of energy equation look like? Okay. Yeah, this is kind of specifically ideal, ideal specifically to the question, what's the speed after moving some distance? If you see that question, what's the speed after moving some distance? Think, I could probably answer that fastest with conservation of energy. Almost. Pretty close there. Right. So here, we get it. Right. Okay. I think if I give you guys another couple minutes, some of you guys get this. Wait, maybe this one's a little tricky. But guys, think of it this way, right? M2 I have is the larger mass. Isn't that going to fall down? And by falling down, it's losing gravitational potential energy. So isn't that sort of like the supply of energy, right? And that energy, I'm thinking, has to go to 3 places. It has to lift the small block. I mean, that's where some of the energy goes, to lifting the small block, right? Also, each block, since it's accelerating, it's going faster, faster, faster. Okay, so it's picking up speed, so that's kinetic energy, and that's for each block. Okay. So let's see, is that what I wrote here? That's exactly what I wrote. Aha. See, the large block falling is supplying all the energy in its gravitational potential. Okay? It has to lift the small block and give each block a speed, so that'd be kinetic energy. Okay. So boom. Okay. And then, right. So if they gave you some values, like I said, told you what the mass of the blocks were, it'd be probably implied that gravity could be Earth's gravity, 10 meters per second squared, and say it falls 40 centimeters. So you put 0.40 meters for h. You can solve for that in v. You do that. Okay. Right. You guys see that? next to? Ooh, this one. This one. Okay. This one's okay. Part conservation of energy, part geometry. Okay. So say given the length of some pendulum and the starting angle from the vertical, let's also throw in gravity field. That's going to matter too. Okay? Right. Can you solve for what's the speed at the bottom? Let's say the maximum speed, which would be the speed at the bottom. Okay. You guys probably remember mass is going to be part of the setup in the equations, but should cancel out, I think, right? The mass of the object. Okay. Go ahead. Now, this one's kind of tricky, so I'll give you guys a little extra time for this one. It's kind of a two-part question, right? You guys got to do the geometry first. So can you handle the trigonometry, right? Figure out a little hint. What is the height change? Has something to do with, I do see kind of a triangle there. You do some geometry to figure out the height change based on L and theta. And once you got that height change, then you can kick over to conservation of energy. It's like a two-part question. Right? If this was a multiple choice question, I wouldn't be completely surprised if AP just went ahead and told you the height change, right? Just kind of skip the geometry part. Okay. But then we just turn it back into like Galileo dropping the ball off the tower, the same thing. All right. Yeah, so Alec got the whole thing. All right. All right, all right. See, some of you guys are on the right track. Looks like. Getting there. Ooh. All right. Let's check this out. Okay. So here, show you the whole thing here. So I would actually start trying to figure out what's this height change. Right. Well, I do see that the length of the pendulum is probably the same. That length should be that length. Right. Now playing off this triangle, this leg of this triangle is L cosine theta. Okay, so L minus L cosine theta gives me the height change. L minus L cosine theta. Okay. If you like, you can factor an L out. It's not 100% necessary, but you could, might say it that way. Right. Then let's kick over to conservation of energy. So yeah, this is actually really similar to Galileo dropping the ball at the tower, right? It starts with potential energy at the top, ends up with kinetic at the bottom, boom, boom, right? And then you go solve for B, right? Just like that, right? If you look at it, it's really the same result too. So it's square root 2gh, but h is this fun expression right here. And then kind of like we were saying before too, what if instead of dropping it, what if you push off? Okay, so then that's how that translates right there. Kinetic energy translates to, okay, yes, all right. That, all right. Oh, yeah, you guys did this. This was a lab. That's right. So I had you guys calculate what should be the speed at the bottom, then use one of the speed gates to actually measure that. Ooh, car brakes to a stop. Ooh, this could be a question. Oh, so set up an open system. Let's say a system that consists of only the car. So a system that consists of only the car. Give you guys another hint. Or maybe I'll ask you guys, if the system is only the car, then what effectively is the net force equal to? The net external force. I see three forces, but the weight and the normal force kind of cancel out. So just friction force, right? Right. Okay, so friction is doing negative work on the car. Right? The guy was driving along with some speed, right? Slam the brake. See if you can figure out what is the braking distance of the car as a function of the initial speed of the car, and I think coefficient of friction is in there. Right? Yeah, this one's a little tricky. So go ahead, give you guys a little time here. So what I'm thinking is, I'm going through this process. I'm gonna start with an open system. Set up an open system. Conservation, but I mean, looks kind of like conservation of energy, but it'd be open. So there's negative work being done on the car. Right? And then can throw in some extra steps. They can figure out what is the braking distance of the car as a function of the initial speed of the car, coefficient of friction. I think gravity field also matters. All right. Ooh. Okay, we take one more trip around the room. See. Ooh, I think that's close because then yeah, it might be actually pretty good, pretty good. All right. All right, so I think you guys are doing pretty good there. Let me see what I got on this poster. Okay. So there's my open system. Right, the car started off with some energy. I guess it would be kinetic energy. Oh, there it is, kinetic energy. Okay. There was negative work done on the car, so I'm doing minus, and then force times distance. Now that is the friction force. I'm just right. Oh, and then the word stop. Right, final velocity is 0. It has 0 mechanical energy at the end. Right, 0 kinetic energy because it's stopped. 0 potential energy because it hasn't rolled up any hills. Right, that could possibly change it too. But all right, so we got this. Oh, ooh, I did a substitution here. Friction force is coefficient of friction times normal. Oh, actually, I did a double substitution. That's what I did from this line to this line. Just trying to squeeze it all into one paper, make it look good. All right, so there's a double substitution from here to here. Friction force is coefficient of friction times normal force, but the normal force is equivalent to the weight. So boom, boom, it's like that. Okay, you can solve for this D. Yeah, the mass of the car cancels out, just like I said it was going to. Right, looks like this. So there you go. There's the braking distance of the car as a function of the initial speed of the car, coefficient of friction, and gravity field. Boom, 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 just like that. Okay, good. Okay. Oh, a really classic question about, I guess there's a little bit different questions you asked about this, right? But a really classic question is, guys, if you triple the speed, the initial speed of the car, you triple the initial speed of the car, what happens to the braking distance? Is that triple, or is it something else? 9 times the braking distance, right? Right, because throw a factor of 3 on that V0, square that, be 9 times the braking distance. Right? Guys, what if you triple the mass of the car? How does that affect braking distance? Wait, what happened to mass? It canceled?
Oh yeah.
Yeah. So triple the mass of the car makes no difference, right? So what if you do both? What if you triple the mass of the car and you triple the speed of the car? Triple the speed of the car makes it 9 times the distance. Triple the mass of the car has no effect at all. Right? Any of those questions are completely fair questions. Right? You could be asking this. All right, let's see what I got next. Ooh, this next one. All right. So let's do power in an elevator. Here, I'll start you off with the formula for power. That's work per time, right? A rate of energy transfer. You can think of it that way. Okay. AP likes this question. I think there's maybe a 50-50 chance you're going to get this question. Okay. All right. So wait, what did I ask about this? Oh yeah, because if you know, here, you guys see my elevator I've got going at constant velocity. Oh, how do I know it's constant velocity? Yeah, exactly. Yeah, because the force is balanced out. Yeah, right. So 0 net force. But it did give it a velocity, right? So it's going constant velocity. So this tension and this cable is equal to the weight of the elevator, right? And there's let's say there's some motor at the top of the shaft, pull up that elevator, that tension. Right? What is the power of that motor in terms of this force and this speed? What is it? Does anybody know the answer to that question? Just offhand? That's it. Force times speed. Boom. Okay. So it's a real short derivation there. Okay. So no, power is actually work per time, right? The rate of work. Now work is force times distance. But if you wrote these two variables together, distance over time, well, there's speed. Force times speed. Right? Yeah. So can you guys hold that formula in your back pocket and pull it out for probably multiple choice? I'm guessing, right? Although I have seen this as an FRQ before too. Okay. You guys do that? Or I think it would never be. Here, I'm just going to show you this next one. All right. I think this full poster is a little bit beyond the scope of anything they would ask, but if you take physics in college, almost for sure you're going to see this. Right? It's like, what's the minimum height of this roller coaster to guarantee it gets around the loop? It's a two-part problem. You have to go back to Unit 3 with centrifugal force. Actually, this question I did ask you the other day is, what's the minimum speed to get around? You guys remember what square root GR, right? About water in a cup on a string and oil there on a vertical circle. The minimum speed to get around is square root GR. Of course, you can go faster than that, but you can't go any slower. and then the second part of this is, well, okay, so what hill height? And that you can do conservation of energy. Right? So, okay, so I did that. And this is the universal answer to that question, assuming that there's no frictional losses, right? But yeah, I think that's probably a little bit more than AP would ever ask you. Here, this next one, I'll just show you the whole thing too. Okay. Let's do, so this is a little bit fancier looking Atwood, a little fancier look Atwood, right? I got these three masses now. And I bet there's different tensions in these strings, so be careful about that. There's possibly a friction force up here if they want to be really tricky about it, right? I can do conservation of energy, right? So what's the big picture principle, like the forest for the trees, how you saw this? Well, if mass C is larger than mass A, then it's going to go clockwise, right? So mass C falling is providing the energy. Now I would subtract out this friction force times this distance moved. All right, so subtract that off, right? And whatever's left over, C has to lift the small block A, and then each of these blocks has a speed and therefore kinetic energy, and they're all the same speed. Right? And this height falling and this distance moved horizontally are also the same, so you can do a substitution there. Okay. There's the forest for the tree setup. Different ways you could go with that question. All right, so are we good? You good? All right, and the rest of these posters, I don't think AP is going to ask at all. They never ask about simple machines or mechanical advantage. I had you guys do this lab because it's a good lab, but right, leverage. Actually, I do have a Unit 7 question about, so it's kind of like that, but we'll save that for Unit 7. Mechanical advantage, yeah. And here's how you go from universal gravitational potential energy to localized MGH, right? All right, so all those I just flipped through real fast. AP is not going to ask about because I've never seen them ask those questions. But yeah, a little extra. It's always good to know a little extra, right? All right. Oh, that was Unit 4. You guys ready to move on to Unit 5? Unit 5. All right, momentum. Here we go. Momentum. All right, so mass times velocity. You guys remember this was a vector value, right? As opposed, like all those posters we just looked at with energy. What was energy, a vector or a scalar? Energy is a scalar, right? Right. So like if you're rocking in space, you have some speed. It doesn't matter which direction you're going. Right? You have same kinetic energy, right? But momentum, this does matter. Say if you have two asteroids that are on a collision course, because we're talking about collisions, right? Whenever you see a collision, think this right here, right? If they're headed opposite directions, that's going to be a different outcome than if they're headed in the same direction. Even to the same speeds, got to care about what's the forward and backward direction. Okay, so we're talking about vector quantities, put little vector arrows, those some variables, right? There we go. So, okay, it should be conserved in a closed system, I should say. All right. Okay, general conservation of momentum. So it's gonna have to know. Here, should show you guys this one. Okay. So momentum is conserved pre and post collision. So if you add up all the mass times velocity that's before the collision and all the mass times velocity that's after the collision, it has to equate. Right? Again, that's regardless of what type of collision it is. Right? So you could have something that's pretty elastic, like that right there is pretty elastic, or you can have something that's not, maybe something like half the plate of tennis balls, right? But this expression will hold true for all different types of collisions. Right? Now the catch, yeah, if it's really elastic versus if it's like less elastic, both of these V's could change, right? Depending on the type of collision. All right, so that'll be it. All right, now, what I got next here? Yeah, let's look broadly type of collisions. There we go, type of collisions. Right. So I got kind of a spectrum here. So perfectly elastic. That's what I just showed you guys with the Newton's cradle. It's really bouncy. Here's just in general. Here's perfectly inelastic. Right. And then you could get an explosion question. That's like a reverse collision. Let me ask you guys what's going on with each one of these. Right. So, guys, for perfectly elastic, let me see. Show hands. Show hands. You guys ready to show hands? Right. Is momentum conserved for perfectly elastic? Yeah. Right. Momentum conserved. Right. How about in general? Is momentum conserved? How many guys say yes? How many guys say yes? Momentum's conserved. Yeah. Right. How about perfectly inelastic? Is momentum still conserved for perfectly inelastic? Who says yes? Who says yes? All right. Right. Now, what about an explosion? Is there a gain or loss in momentum, or is momentum conserved for an explosion? How many think it's conserved? Who says it's conserved? Still conserved? Still conserved? Right? Yeah. Okay, you guys got all those, right? Yeah, guys, every single one of those scenarios, momentum's conserved. You guys got that? Sometimes say explosions like a collision in reverse. Okay. Right, how about kinetic energy? Now this one could possibly be different, maybe depending on what's going on. Right, so perfectly elastic, like Newton's cradle I just showed you. What happens to kinetic energy before and after the collision? Does it stay the same, go down, or go up? Who says kinetic energy is conserved for elastic? Conserved for elastic. Who says that? Who says that? Yeah, actually, that's what defines a perfectly elastic collision. That's the only type of collision where kinetic energy for the system happens to also be conserved, right? You might have to write that out in a sentence for an FRQ. Hey, how do you know it's elastic? Oh, kinetic energy is conserved. What can you say about the fact that it's elastic? Kinetic energy is conserved. Perfect collision, right? What about in general? In general, just a general collision. Say you got two half-deflated tennis balls. What happens to kinetic energy? Yeah, there you go. Yeah, less than, or yeah, you could throw in a possible equal if it happens to be elastic. That's true. Yeah, less than, right? Okay. How about perfectly inelastic would stick together? What always happens to kinetic energy? Yeah, always goes down. Good. And what about an explosion? Goes up. Because that energy maybe comes from, if it was a grenade, maybe there's some chemical reaction, and that's where the energy comes from. Yeah. So if you measure the mechanical energy before and after, it's gone. Okay. Hey, you guys got that? All right. Let's see what I got next here. Right, perfectly inelastic collision. I did want you guys to write this one down. So go ahead on your paper, write down the conservation of energy. Sorry, momentum, conservation of momentum. Okay, give you guys that much. Right, for that type collision in terms of mass A, mass B, velocity initial, velocity B initial, velocity final. There's 5 variables. Okay. Write down the conservation of momentum for that one. Okay. Almost guaranteed you're going to get this question. Okay. Actually, I would be really shocked if they did not ask you this. Yeah, AP likes to ask conceptual questions if they can, but every once in a while they'll throw you kind of a math question where you solve with numbers, and they like to do that with this one. All right, so Alec got it. Yeah. Okay, Catherine got it. Connor got it. All right. So you guys said, so each one just starts out with its own momentum, MA, BA naught, MB, B naught, add those together. Right. Oh, I guess before they collide, maybe you don't know. I mean, it could be any kind of collision going into it, right? But then, they did stick together. Yeah, the fact they stuck together, they made one giant mass. MA plus MB. They have the same final velocity. Boom, boom, boom. Right. Again, this is one of the ones where AP likes to actually throw you some numbers and say, solve for the final velocity. You do that. This next one I'll show you the whole thing. So perfectly elastic. Now we're back to Newton's cradle, right? AP is not going to have you solve this gold box, but they might. Or wait, actually, here. Here's what I have seen them do, and we've done a few of these in class. There might be a multiple choice question where sometimes the fastest way to answer it is to just play off your multiple choice answers, right? Like they might say, this is an elastic collision. Which of the following could be the final velocities of these objects, right? Now you could test conservation momentum, but that's not particular to elastic, right? I would maybe more focus on kinetic energy. Say, is the kinetic energy before equal to kinetic energy after? So they give you the masses of the objects, boom, 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 and also the initial speeds, boom, boom, and final speeds, boom, boom. Then you could say, is this number of joules before the collision equal to the number of joules after the collision? So if you get like 14 joules here and 14 joules here, you're like, okay, well, it cleared that test. And maybe want to make sure it also clears that test, right? So we can, right? If this was a free response question, then they might say something like, what makes something elastic? And they say, oh, kinetic energy is conserved during the collision. Boom. And that's probably what they're looking for. Okay. All right. If you take physics in college, hold on to these notes because this will save you a lot of paper and a lot of time. This gold box right here. You don't find that in a lot of textbooks. Oh, yeah, this next one. Here, let's just look at this whole poster here. Oh, what if I got something that's inelastic, like here's a bullet that embeds in a bowling ball, versus something that's elastic, like this bouncy ball. Bowling bounces off the ball, right? Now, guys, which one of these gets the bowling ball rolling faster to the right? The inelastic or the elastic? Let me see. Show of hands. How many guys think if you throw a radar gun on the inelastic, the bowling ball is going faster? Who says the elastic is rolling faster? Yeah, that's what I'm thinking. Right? It could be up to twice as fast, I think, up to twice the momentum transfer, right? Because guys, this bouncy ball, suppose this bouncy ball is coming in at like 10 meters per second. When it Boeing rebounds, it can go up to 10 meters per second in the other opposite direction if the bowling ball is really massive compared to the bouncy ball, right? So kind of a boundary asymptotic condition, right? Guys, what's the difference between 10 meters per second to the right and 10 meters per second to the left? And don't say 0. What's the difference between 10 and negative 10? 20. Right? Then multiply by the mass of the bouncy ball. Right? Now that's the momentum that's just been transferred. Right? You guys see that? All right. Okay. So. Okay. Lab table. You guys remember those collision parts you guys had? Had you guys bounce them off each other and then put on magnets and they stick to each other? Let's see. AP's not going to ask this. Yeah, the only way they would ask something like this is if they set up the context. They wouldn't expect you to necessarily come in knowing this. And so I doubt you're going to quite get that question. Okay. Although that made a pretty good lab, though. Okay. Oh, yeah, that's right. Here's a closed and open system from a momentum point of view. Right. So I told you the energy point of view, told you the force point of view. Yeah, there's also this momentum point of view, right? Okay. So closed versus open system. This next one, it actually is important. This got shuffled on those other posters. All right, impulse. Okay, guys, impulse. I've got part of this graph covered up. This graph is force versus what? Time. Force versus time. Boom. Right? So, hey, look, it's a collision situation again. Right? That hits a ball. Boom. Okay. And this time, I put delta t like a time interval. Usually for these type of questions, that it's really small, maybe like 1/10 of a second or something like that, right? So just real tiny time interval. Doesn't have to be, right? Maybe another example is you could have a rocket through space that blasts its engines with some blast force for some time interval that could be a lot longer. That's okay too, right? But yeah, force times time is going to result in an impulse. It's a momentum change. Right? So then, say a bat hitting a ball, if you know the mass of the ball and you know this impulse graph, which is this part right here, right? You can figure out what's the change of velocity of the ball, right? So if the ball starts on a t, then the change of velocity, let's say it starts at rest, right? Then the change of velocity would also represent the final velocity of the ball, right? But if the ball's coming in at some velocity to the left and you hit it back to the right, I asked you guys the same question I just asked a minute ago. What's the difference between 10 meters per second to the left and 10 meters per second to the right? It'd be 20 meters per second, right? Right? That's what that delta V would be right there. So got that. And if there was a rocket blast in its engines and they gave you this type graph, okay, you integrate the graph, you get that bit, right? That green triangle there. And then if you know the mass of the rocket, you just divide that over and get the change in speed of the rocket. All right, you guys good with impulse? What's here? Ooh, ballistic pendulum. All right. If AP asked this might be like the hardest question they could ask, but I think it'd be in the realm of fairness. So usually the question goes, if you know the length of this pendulum and the mass of this block and the mass of the bullet, and you know how high it swings up to, if they want to be even trickier, they might just give you this angle and have you calculate the height change. Did that earlier today, right? Some geometry. Then the question would be, what was the firing speed of the bullet? That's the classic question, right? Now, you could rearrange that, right? They could give you the firing speed of the bullet and say, how high does it swing up to, right? That'd be just the reverse, right? But I think this poster, the way I solved it was to answer the classic questions. What was the firing speed of the bullet? Which means you solve this whole thing backwards because that's the first thing that happens, right? So the last thing that happens is it swings up some height. So guys, a height change for a pendulum, if you see a pendulum with a height change, does that sound like conservation of energy that we were just looking at before? The guy swinging on the vine? Right? I think that's what's in this green box. Yeah, that is that. Conservation of energy. Right? So I can figure out how fast post-collision, like after the bullet embedded in the block, did the whole bullet block together start swinging up? That's what that is. Oh, and look at that. It's square root 2gh, just like Galileo dropping the ball for power. Boom. Okay. Okay. Now we got to go a step back in time before that and say, well, what initiated that collision? And that's going to be not conservation of energy, but conservation of what? Momentum. Boom. Like that. Okay. Here, see if you guys get this one. All right. So on your paper, write down what's the next line that I've got covered up. Cover up the next line. What's that next line I got covered up right there? All right. It's working there. All right. So conservation of momentum. All right. So here's what I'm thinking. I'm thinking that right before this bullet collides with the block, it's got its own mass, little m, and some speed that ultimately we're solving for. Because again, that's the classic question, right? That's the initial momentum. After it embeds in the block, hey, that collision is perfectly what? Elastic or inelastic? Inelastic, because it embeds in the block. They stick together. So yeah, that could be like that, couldn't it? Right? So mass times speed of the bullet, and remember the ultimate question is what's the speed of the bullet? So we're trying to find that. Is okay, the two put together, the block plus the bullet, and then they get to swinging together at some speed. How fast? Oh, well, that's what we answered back up here with conservation of energy. That substitutes right there. You guys that? Right? And then to find the firing speed of the bullet, all you have to do is divide by the mass of the bullet. Boom, boom. There's the answer. Right, you guys see that? Right. Yeah, the one trickier step they could go with that is they could calculate, they could have you calculate this height change based on this L and this theta. And you guys remember what that is? H is equal to L times 1 minus cosine theta. We looked at that earlier today. You guys remember that? Swinging on a vine. All right. And then, okay, in 2 dimensions, they're not going to ask you 2 dimensions, so don't worry about 2-dimensional collision. All right, that finishes Unit 5. All right, you guys got any questions on Unit 5? You guys doing good? All right, let's go on to Unit 6. You guys ready for Unit 6? Get these posters back in sleeve. All right, Unit 6 time. Hey, classic pendulum. All right, you guys remember? All right, so pendulums, periodic motion. Actually, I remember there were blocks on springs. You guys remember that too? There were 2 main categories of harmonic motion for this Unit 6. You've got pendulums and blocks on springs. Right. There were a couple other scenarios too. I remember something about like an ice cube bouncing up and down inside a glass of water or something, and little questions like that. But usually it's pendulums and blocks on springs. Right. So time period is swing back and forth. So got 2 pi times the square root of L over G. Guys, if this is a free response question, I've seen AP wants you to specify that theta is less than 15 degrees or something like that. Can you guys say that if this is a free response question? Can you guys specify theta is less than 15 degrees? Because that'll pick you up a point. So it's one of those little details, right? Okay, string is negligible mass, so all the mass to be in Bob here. Okay. Let's go through some proportional questions. Guys, what if the string is 3 times the length? Right, so you have like 1 meter versus 3 meter string, right? And then like some bob on the end, it's like a kilogram. Right? What's the new time period? How many times as much? It's not 3 times as much. Who knows? Who knows? Does anybody know this? Guys, here, let me say it again. So what if you triple the length of the string? So you had a 1 meter string, and now we're going to make it a 3 meter string. Or still put the 1 kilogram at the bottom. Okay. Guys, if it's 3 times the length, that's how many times the time period to swing back and forth? It's not the same time, and it's not 3 times the time. Is anybody going to get this? Three times the length is how many times the time period? Huh? You said what? Square root 3. Aha, Eli got it. Square root 3. Yeah, which is about 1.7 something. Yeah, square root 3. Because if you throw a factor of 3 on that L, notice it's underneath the square root. Yeah, so it'd be square root of 3, which is like 1.7 something. Right. Here, just more like proper, because normally that's what I do. So I just point out, hey, that factor there is under that root. It's going to have that outcome. Right? But what if I write this out? I'll say like some t initial is, say, 2 pi times the square root of L over G. G could be maybe Earth gravity if you like. You need a number for that. Right? I'll say T nu is 2 pi times the square root of 3L on G. Okay, so what is T nu in terms of T naught? And it should be the square root of 3 times, but let's see if that is. Right. Ooh, can I divide one equation by another equation? Can I do that? Is that okay? Right. So I'm getting the ratio T naught over T nu is, right, the 2 pi cancels, the square root 1 over G cancels, square root L cancels. This looks like 1 over the root 3 like that. I can cross multiply. So that gives me square root of 3 times the original time is equal to the new time. Yeah. All right. That's what Eli said the answer was going to be right there. Right? Boom. There's a little proof for it. Right. Next question. What if you have pendulums in different gravity fields? Or what if you put this in an elevator? Right? That would feel like somebody just changed the gravity. Right? What if you have 3 times the gravity field? 3 times the gravity field. What happens to the time period? Changes by a factor of what? 3 times the gravity field. Yeah, there you go. Yeah, square root of 1 over 3, or 1 over the square root of 3. Yeah, that'd be it. So, what? Actually, I don't even know what that is. I should know. Let's see. Calculator. So the square root of 3 is, yeah, 1.73 something. What is 1 over that? Like 0.577 about. All right, there you go. Okay. What if you go from a small mass to a large mass? What if you triple the mass? Yeah, 3 times the mass. What happens to the time period? Yeah, it stays the same. Yeah, doesn't change at all. Right, you guys got that too? Right, are we good? Right, any questions on pendulum? All right. We got some other pendulum questions coming up, but get more go. All right. Non-bomb pendulum. All right. They're not going to ask you this, but a little extra. So you guys did this lab. Remember how you split up into different groups for different independent variables? This next one I think is good to know. Let me cover this up here. All right. Let's get some graphs. Pendulum lab graphs. Let's see, what does it have new graph here? Let's see what's under this paper. Okay, got. Yeah. Let's set up 4 graphs here. All right, you guys on your paper set up 4 graphs. 4 graphs. See how many guys get these right. All right. So it's pretty much what we've just been talking about last few minutes, but see graph formulas. So are these all? Okay. Let's do time period in seconds versus mass in kilograms. Let's do time period in seconds versus angle in, say, degrees. Let's do time period in seconds versus length in meters. And how about time period squared versus length in meters? Let's be square seconds here. Yeah, right. Go ahead. Draw those 4 graphs. This would be a really good free response question. I might be waiting for you. Be sitting a stack of papers. 4 days from now, might get this exact question. They draw those graphs. Those are the formula we were just looking at, right? All right. See some winners out there. Let's check this out. Check this out. There you go. There's the answers. Right. Yeah. So you guys were getting these. You guys said no relationship with mass or angle. Right. So you change the angle, change the mass, the time period is the same. Whatever. No relationship. Right. Now time period versus length. That's a square root relationship. Right. Isn't that a square root curve right there? Time is proportional to the square root of L. Right. And then now if you square the t. Okay. Let me go back to. That's kind of over here. Right. Like if you square both sides of this equation, then it's CB value, right? So maybe time period squared equals 2 pi quantity squared times, and then just plain L over G because that root goes away, right? So time period squared is proportional to L. And that's exactly what this shows. Ooh, who could tell me, guys, what is the slope of this line equal to? You kind of see it right here. Like if I take this expression and I square both sides, isn't that t squared equals 2 pi quantity squared times plain L over G? The root goes away, right? That's true. Right. And then this graph, that's just, here's the y-axis, here's the x-axis. Right? Is that true? Right. And then, right here, here's the slope. Right? So let me write that a little bit different. Time period squared equals 2 pi quantity squared on G all times L. Is that like y equals mx? Here's your slope right here. 2 pi quantity squared over G. That's the slope of that line. Right, you guys see that? You see that? Right. Suppose you had the axes scaled, have some numbers, you have some points, some coordinates, right? You find what's the slope of that line, you get a numerical value, right? Can you set that numerical value equal to 2 pi quantity squared over G and then solve for G? You could do that, right? Little algebra, right? Figure out what's the gravity field of the planet that I'm on. Let's get that. All right. Let's see what's next here. Ooh, block on a spring. Block on a spring. Again, this is the other main category questions from this unit. You guys remember 2 pi times square root of m over k? Guys remember that? We did some labs where they did this. So here, same thing. Let's look for proportional changes. So what if you triple this mass? Guys, triple this mass. What happens to the time period? Yeah, square root of 3 times. So like 1.73 times. Right? What if you make this spring 3 times as stiff? It's 3 times the k. What happens to the time period? Yeah, square root 1 over 3, right? So we say like 0.577 something, right? So what else could they ask you? What if you triple the gravity field? Guys, if you triple the gravity field, what happens to the time period? Yeah, nothing. Doesn't change at all. Right? So yeah, so this would look the same on Earth as it would on Mars, right? So gravity field's not part of that equation. And I know something else AP likes to ask too. I remember what AP likes to ask, right? Is what if so what if it's just hanging there at equilibrium, right? You guys see it's hanging there at equilibrium, and you pull this down 1 centimeter, you let it go. It starts to oscillate. Suppose it takes 5 seconds to oscillate, right? One time period. Then you're gonna triple that amplitude to 3 centimeters. Remember, before you only pull it 1 centimeter. Now you pull it 3 centimeters, let it go. What happens to the time period? Is it more time, less time, or the same time? Same. Yeah. Because amplitude is not part of that expression. I've seen AP ask that question a number of times in the past. There's a good chance you're going to get that exact question. Okay. You guys good? Ready to fill that? All right. Oh yeah, I had you guys do a pretty extensive lab on that. Right. Let's go. Oh, this next one. All right. Yeah. Okay, now this next one's a little more involved, but there might possibly be an application to this. Right. So here goes the scenario. You got a whole story. Right, you guys ready for this? Gotta follow this one. So suppose I got some spring, it's just hanging there from the ceiling, and there's nothing on it, and it's a really lightweight spring. Okay, so guess its dash line. Right, so that's like unstretched. So, okay. Then I'm gonna put a weight on it. I'm gonna very carefully lower it to an equilibrium position. Okay, and it's stretched by some amount x equilibrium. Okay, so that's all fine and good, right? Right, it's like 5 centimeters or something. Okay, now what if I take the weight off and I'm gonna reattach it like right there, reattach it right there. And then I just drop it and let it go. Does it overshoot the equilibrium and stretch way beyond that? Yes, it does. Right? And who remembers? Maybe you kind of memorized this possibly. Right? What is this maximum stretch compared to this equilibrium stretch? Does anybody remember what that ratio is? Double. It's exactly double. Yeah. Right. And how can you prove that? Like for equilibrium, guys, what process in physics do you use for equilibrium? Forces or energy? Forces, right? Versus if you ever get a question like what's the maximum stretch of a vertical spring, that's going to be a what type of question? Energy. Right. All right. So I got all of the math to back up everything we just said right there. I'll walk you through that too. Again, this was a little more involved, and there's a pretty good chance this is gonna be pretty useful in 4 days. Right. So equilibrium. So net force is equal to 0. Okay, got the weight down and the spring force up. That's Hooke's law, isn't it? This x is the equilibrium x. Right. And you can solve for that and get mg over k. Boom. There you go. Weight divided by spring constant. Right. All right. But if you said something about conservation of energy, okay, playing off, say, this top line here, it could possibly drop some maximum height. Okay, so I'm going to treat that as the height that it could drop. Right? So mgx max. You guys got that? Like mgh, right? And that stretch amount, okay, well, that would be the energy in the spring, 1kx squared. And it's the same x, right? Is it? Right, so one of those x's cancels. Solve for x, and you get 2 mg over k, because this 2 cross multiplies, right? And that's double that. Boom, boom. All right, you guys ready to fill that one? All right. All right, I got next here. And I'll just show you guys this one. Right. So you guys remember frequency and time period are reciprocals. Right. I'm gonna ask you guys a question that's on my honors final exam. Right. Okay, suppose there's a leaf on a pond, and you're watching some ripples go by in the pond, and you're watching the leaf bounce up and down like boink, 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 boink. You guys see that? Okay. Suppose it's like two bounces per second. Right. That would be a frequency of what? Is that 2 hertz? Right, 2 hertz. Right. And what would be the time period between bounces? Half a second. That's exactly what these two say right here, right? Right. So 1 over 2. Right. So half a second, 2 hertz, they go hand in hand. Right. All right. This angular frequency, this might possibly be helpful. Right. So suppose you take that frequency, whatever it is, right, and you watch this oscillatory motion. If you multiply by 2 pi, you get what's called the angular frequency. Notice this is not angular velocity, although we use the same character for it. Right. It's a different concept. Right. And that's really a setup for this next poster right here, which is you can make graphs out of these, right? So playing off here's the angular frequency, you can very quickly put together these graphs, right? Alternatively, you can just play off the regular frequency and just pop in the 2 pi yourself. You could do that. It's all embedded in that. You guys see that, right? Now, more often than not, x versus t starts with a cosine because it starts with some initial displacement. Oh, here's your 2 oscillatory, your 2 main oscillatory scenarios, right? Right. Got the pendulum and the block on spring, right? So I pulled it back, gave it some displacement, let it go. It's gonna oscillate back and forth, right? Right. Now here's where, I know all my calculus students are gone right now because they're all taking the exam, right? But if you're in calculus, then you see, remember something called chain rule that can tell you how to go from displacement to velocity and velocity to acceleration, right? The fact that this angular this angular frequency, I meant to say, right, comes out in front, right? So it was it. Anyway, there you go. It goes from cosine to negative sine to negative cosine. And then, do you guys remember this real trivia? What is the rate change of acceleration called? It's called jerk. In this class, we'll just set that equal to 0. Right. But for oscillator, there could be a fourth graph after that, right? And that goes back to positive sine, and then the rate change of that is positive cosine. So it's like a 4-part process, really. Okay. Cosine, negative cosine, positive sine, then it goes back to cosine. All right. Okay. Anyway, a little bit. Here's a fun tidbit: is if you're watching springs, let's say a vertical spring and a horizontal spring, right? You're watching these two blocks, so like wow, 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 wow. Right? If you look at their position versus time, and I've seen this called like in phase space or something, I think, right? It'd be like if you have a car driving around at circle at constant speed, right? These coordinates will always line up, right? This is like sine and cosine. It's the same idea. All right. This next one. All right, you guys ready to write some stuff in your notes? Okay. Let me see. Okay, so for this pendulum or for this block on a spring, okay, really similar formulas we've been looking at. Right? How can you linearize this data? And there's several answers to this. I just put a couple on this particular poster, but really there's several ways to do it. Let me give you guys some time. So you guys go ahead, figure out at least some way to do it. Some way to do it. We'll come up with a few solutions anyway. How can you linearize this data? There's different ways AP could possibly throw this at you. They could throw you tables of data, possibly. They could ask for, hey, what's the gravity field for this pendulum? Or they could say, what's the spring constant for that spring scenario? Right? Those could be questions. Right? They might want you to solve that from some property of the graph, probably something to do with the slope, right? And something like that. So you could do this. Okay. Let me start writing out something myself. I forget exactly what my solution is on the poster, but see what I come up with here. So I'll do it for the pendulum. See, I could square both sides. That would probably be helpful, right? Especially if I was trying to answer a question like, what's the gravity field? Or something like that. Okay. Okay, now here's where maybe I got some options. Okay, so I could go t squared equals 2 pi quantity squared over g times L, right? That should be one way to do it. I could make a little graph here. I could go t squared versus L, and these points would line up in a straight line. And the slope would represent 2 pi quantity squared over g, right? See, what else could I do? I could flip the axes. I could go L equals g on 2 pi quantity squared times t squared. Right? Flip the axes. Right? And if this was a multiple choice question, then see the first way I did it, the reciprocal of the slope of this line would have something to do with the gravity field. And the way I'm doing it right now, if I flip the axes, I put L here and t squared here. Right? I just get the reciprocal of the original slope. So now this is g on 2 pi quantity squared, right? So something like that, right? So that's that one. I could take the 2 pi quantity squared and I could embed it in one or the other axis. So what if I do that? How about this? What if I cross multiply the 2 pi quantity squared? I do 2 pi quantity squared times L and make that my entire y-axis, just embed that straight in the axis. I could do that, right? And the advantage of doing that, actually, that'd be really nice because now the slope of that graph would be exactly the gravity field, and I wouldn't have to do any extra manipulation. I could just get the slope of that graph. Right, let me draw that graph for you guys. So that would look like 2 pi quantity squared times L. And then I'd have t squared on this axis. So I got crazy manipulated axis, crazy manipulated axis. Okay. All the point, like if you had a data table, all the points would line up on a straight line direct relationship. And very conveniently, the slope of this line would be exactly the gravity field. Right? So I could just find the slope and be done. Right? See, it's like y equals slope times x, right? Y equals mx kind of deal. Right? I see that. Right? Everybody see that? Right? And okay, and I guess the fourth way I could do is I could take the 2 pi quantity squared and I could divide it down and embed it in this axis. So I could do t squared over 2 pi quantity squared. I could do it that way too, right? And the slope would still be g, right? I get that, right? Right. Did you guys come up with at least one of those? Or you guys think you could figure that out? Do at least one of those? Right. Now, what did I put on this poster? Okay. All right. So I did that, and okay, then the spring version is really similar. Okay. So again, those aren't the only answers, but those are a couple ways to do it. Okay. So you guys know AP loves linearization. So that whole process we just did, there's a bunch of graphs that could possibly apply to, right? Anything that's like a parabola graph is definitely fair game to be linearized, right? Just square one of the axes, right? Just like what we did. All right. What's next? Oh, okay. Maybe I'll scoot through the rest of these posters real fast. Okay. AP's not going to ask that. They used to, but not after 2019. No, no. Yeah, all this is just for my honor students. I think I had you guys do this lab anyway because it's fun. But yeah, this is just for my honor students. AP is not going to ask about any of this. Okay, again, if it was 2019, they would have asked that question possibly. But Doppler effect, no. Sonic, musical. Okay, yeah. Right, so all these we're going to skip. All right. All right. So that was unit 6. Ooh, we got 1 unit to go, and it's the big one. It's unit 7. So it's kind of like everything we've done times 2. Right. Get these posters back in the sleeve. Get in here. There we go. All right. All right, you guys ready for rotational dynamics? Right. Oh, I threw in rotational kinematics also. Kinematics, dynamics, it's all here. Right. So start with the rotational analogs. So everything we had in linear, well, there's some kind of rotational equivalent. Right now, time is still time, so that's okay. Right? It says saying how far in meters. Now I'm just interested in how far is a turntable turned in radians, possibly, or you could say degrees. Right? Radians is really nice if you're directly multiplying it in an equation. Instead of how fast is a car going in meters per second, say how fast is a turntable turning in radians per second. Ooh, I bet Earth turning 1 rotation every 24 hours. I bet you could convert that to radians per second, right? Do that. Instead of a car speeding up or slowing down, we can have a turntable speeding up or slowing down, spinning, radians per second squared. Okay. Okay. Now the top half of this table is like kinematic, right? You guys see that? Now the bottom half of this table is now we're going to bring in. Well, this is the dynamic half. Okay. So in place of mass in kilograms, now it's how massive, but also how is that mass distributed? So the sum of them are squared, right? Right, because we got kilogram meter squared. So capital I could be rotational inertia, right? So if there's a turntable just sitting there and it's made out of like thick wood or something, right? It doesn't have to be rotating. It already has some rotational inertia about its central axis or about some axis. You do have to define the axis. That's okay, right? Or if it is rotating, it doesn't matter how fast it's spinning, right? Kind of like it doesn't matter how fast a baseball's thrown or hit. It has whatever mass it has. Right? Okay, so rotational inertia. Okay. Here's Newton's second law of motion. F equals ma. Here is the rotational equivalent. It has something to do with torque. Right? What forces are to linear, torque is to rotation. Right? Now torque is r cross f, but that results in some I times alpha, and that looks like that. Right? Then there was momentum. So linear momentum, mass times velocity. Angular momentum, capital L is I times omega. And then kinetic energy, 1/2 mv squared on the linear side, 1/2 I omega squared on the rotation side. Boom, 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 boom. Right, that's all good. Right, so know those. Right. 3. Oh, actually, I think I asked you guys to write these the other day, so let's get through those. Right. So 3 rotational kinematic formulas. Right, they look like the linear ones, right? But for rotation, right? So how far something turned in radians, how fast is it rotating in radians per second? Right, here's time in seconds. Is it speeding up or slowing down spinning in radians per second squared? Okay, so that's all good. Okay. I think you guys saw this one also the other day. When we did unit 3, I touched on this stuff a little bit. Okay, so here's how you can translate linear to rotational back and forth for, say, a turntable, right? Suppose you got different oh, hey, I got my Roosevelts right here. Boom, boom, boom. Got these 3 Roosevelts. I get this turntable spin. Right? Now they're all doing the same turns per time. So they all move the same angular displacement. It's up time interval. They've got the same angular speed. If it's speeding up or slowing down, that they're all these 3 Roosevelts are all the same too, right? But the further out they are, the more drastic is their linear motion. Like the sky in the middle, in a linear sense, isn't moving anywhere. 0 meters per second speed, right? 0 meters displacement, right? The further out they are, the further going, faster they're going, and the acceleration, tangential acceleration, I should say, also, right? It's got that. It's proportional to r. So now you can go back and forth between angular and linear values on a turntable, right? I asked you guys to do this one the other day. What turntable slows to stop? You draw these 3 graphs. Right? Again, unit 3 touched on this stuff, right? So here's slows to stop uniformly, right? So negative acceleration, negative angular acceleration, right? And then theta versus t. It's like this upside down parabola, right? That's slowing to a stop. That. Okay, rotational inertia. Oh, I still got these 2 rotational inertia sticks right over here. You guys remember I passed these around, right? And they were the same mass, right? But the mass was distributed differently. So if you push it out like 3 times as far, you're gonna get like 9 times the inertia, right? From rotating, trying to do this with it, right? You guys remember that? Right. Right. And then what about like some common Rayleigh type shapes? Right? So for a single point mass, m r squared, a ring is also the same thing because all the masses on the ring, so, right, as long as it's rotating about the center of these 2 equivalent scenarios. Right? Now, if it's a solid disk, so mass distributed closer in, hey, this is like the turntable, isn't it? If I just turn this vertical, right? It's the same thing as a turntable. 1/2 m r squared. That's a really common one, right? Yeah, that one's pretty common. So is the solid sphere is pretty common. The 2/5 m r squared. Right? Now, you would not be expected to memorize this table. If AP asks you a question about this, which they could ask a question about it, but they would have to give you these values, right? So you wouldn't have to memorize a 2/5 m r squared for a marble or something, right? But they could possibly give that to you. Right? Parallel axis theorem, AP does not ask about. I think they're going to start asking next year, though. Right? So here, just real fast, so you can compete against the next cohort of students. So if you spin this basketball on your finger, that's 2/3 m r squared, right? Which is fine. That was this one right here, right? But what if it's like revolving around this axis that's parallel to its axis, hence parallel axis theorem, right? Oh, you just tag on md squared. That's it, right? That's all you do, right? And it's particularly useful of balls like rolling across the floor, because notice it's not actually spinning about its central axis. It's actually spinning about this point down here. Right? So a little bit different inertia from that point of view. All right. So it's a little bit beyond the scope of what AP is going to ask. Ooh, torque. Torque. Right. So guys, I got 2 formulas for torque. Right. Torque equals what times what, or also what times what. See if you guys get this. Go ahead, write that down on your paper. Right. There's 2 perspectives on torque. You're going to be asked this, right? And probably have to set those equal to each other and solve for things, right? Yeah. Okay. So everybody got this, right? Everybody got the 2 formulas for torque. Okay. So you guys got torque equals r cross f, and now the cross product means perpendicular components, sometimes represented with sine and theta if it's the angle between the 2. Okay. Torque is also I times alpha. That's like Newton's second law of motion, but in a rotational context. Okay. And you can do r cross f as I times alpha. Okay. You guys do that? Okay. Now, careful, guys. What if instead of this blue theta, what if they give you this angle right here from the perpendicular? This, maybe I'll call it alpha or something, right? Is this sine anymore, or is it now cosine? Yeah, right. This would change to cosine if they give you the angle from the perpendicular, right? And so careful about that. Sometimes you'll see that, right? Right. Ooh, yeah. Do you guys remember this lab? Hey, I'll ask you guys a question about this, right? So let me remind you guys what was going on. You guys ready for a question? Right. So remind you guys what's going on first, right? I would hang different lab weights here, right? We had different lab weights, had small lab weights, medium lab weights, big lab weights, right? Let this fall down. Now, here I got a middle step question. Guys, what was the tension in the string compared to the lab weight? Was it exactly the same? Was it a little bit less? Yeah, the tension's a little bit less than the weight, right? Because the weight is accelerating down, kind of like a downward accelerating elevator. So, right, so that was an extra middle step to figure out what actually is this tension that's providing this torque. Ooh, be almost the weight. You could kind of round it to it, but a little less. Right. And so that was one step we had to get out of the way. Right. Then we watch this thing rotate. Now, if it starts from rest and starts spinning and then speeds up spinning, so it's just faster, faster, faster. Right. See, if you know how fast it spins after some time, starting from rest. You could do kinematic, and you could get, what is this, alpha, right? What is the angular acceleration? You do that, right? And now we can start to put this together. Because if you know the tension of the string, and you know this angular acceleration, then there's a way you can find what is the rotational inertia, that's capital I, for this whole crazy pipe system. Looks like a T shape, right? Maybe if I put different weights on here, it could work out differently, right? So here's the actual question I have for you guys, is what was the final graph that we drew on this lab? Right? Like what were the axes? What was the shape of the graph? And the question is, what's rotational inertia? Well, let's see if you guys get this. It's on your paper, write down set of axes that could answer the question, what is the rotational inertia of that crazy looking pipe system? Right. What variables did we put on which axis to answer that question? What is the rotational inertia of that crazy pipe system? I think this could be maybe a more challenging type pre-response question. Yeah, but this could be within boundaries of AP. You ask you this. What is the rotational inertia, capital I, for that pipe system? Almost. All right. Okay. Yeah, this one's a little tough. I see some of you guys kind of on the right track, I think. Oh, where's my ruler? Just have it right here, right? So here, I might write it down here. I know torque is R cross F, right? So the radius of the central pipe could be the R, and then the tension of the string could be that force, is that tension force. And the other perspective on torque was I times alpha. And hey, if the question was, what is I? I bet this is going to be really handy right here. Hey, can this be like Y equals MX? Is that like Y equals MX? Right? I think that's the answer. I think that's it. So doing torque in oh, what unit, guys? What's the unit for torque? What's the unit for force? Newtons. What's the unit for radius? Meters. Put it together. Newton meters. 8 meters torque. And then can do angular acceleration right here on the x-axis. And what's the unit for angular acceleration? Radians per second squared. Oh yeah, it's like speeding up spinning. Okay. And I remember when we made this graph, these points did line up on a straight line. There was also an intercept. Okay. So first of all, what property of that graph tells you rotational inertia I? The slope of that graph, the I right here. Okay. Because if AP gives you the axes backwards, which could maybe kind of make more sense than a cause-effect sense, like if they put torque down here on the horizontal and angular acceleration on the vertical, could you say that the reciprocal of the slope could represent the rotational inertia? Yeah. They could ask you that. They could. Here's the other question I got for you guys. What does that intercept represent? Represents something. Yeah, exactly. The minimum torque to get it going in the first place. I'll call that frictional torque. Exactly. Right? Now, because if you're not sure, then let's reason this out. Say, if I put on some torque and it had 0 angular acceleration, that's what that would mean, right? And if I put on less torque than that, it's not gonna set. Oh, that's right. I remember. Because we did this lab, and for the little tiny lab weights, it wouldn't spin at all. I said, well, why would, because there was a little bit of friction. And that's exactly what that represents. You have to overcome that frictional torque to get it going. Right? So you guys get there. Equilibrium. Let's do 2D equilibrium. Guys, write down the conditions for 2D equilibrium. Something's in equilibrium. So The first weight was probably about October-ish, was September, October was the sum of the what goes to zero. Forces, right? Some force goes to zero, right? And then when we got to December, we added on another condition. We said the what is also zero. Okay, yeah. So forces in each direction, that's true, right? So x direction, y direction, right? But unit 7, guys, what's the rotational dynamic version? That aspect. Say that the torque also goes to zero. Yeah, so the force go to zero each direction. That's true. The torque also zeroes up. The idea being, here, I think I've got some posters coming up where that'll be more clear, right? Right. Good. And then in 3D, you got 3 axes, then 3. Okay, so if you do like engineering school, then you're going to see the 3D version of this also, right? But AP is probably going to stick to 2 dimensions. Okay, so boom, boom, boom. Just know that gold box is there. All right, so let's look at some examples of that. So like this one right here, for example, seesaw equilibrium. Say if you had a mystery weight, that could be a good question. It's like, what is this weight now here? Clearly it's 3m, but what if you have a known weight, right? Like I know what this guy is, right? So it says it's stamped on there, but I got some mystery weight here. I don't know what this guy is, right? So you slide it around and take fine. This is something I've actually done. Like this is good practical knowledge too. Okay, it's like how can you figure out what is that weight? I could do the sum of forces goes to zero for equilibrium. I mean, talk about equilibrium, right? But that wouldn't be very helpful. Here's why. Because I got some known weight down, got some unknown weight down, and there's some support force up that they didn't actually label on this diagram, but isn't true this pivot pushes up on this stick, right? Okay, that would be, no, since these are labeled, who can tell me, guys, what is the upward force actually from the pivot? It's equal to what? Yeah, 4mg, right? And that satisfies force equilibrium, right? But if you didn't know what this large mass is, then that wouldn't really be helpful, right? What would be helpful is this last condition, is that the torque goes to zero. And this is what you use to solve this, okay? So remember when you guys did this lab, so you can pick any point as the pivot point, but some points are maybe a little bit easier to work with, right? It may be more intuitive anyway, right? So if I pick this pivot as the pivot point, right? Mathematically, that's convenient because the upward force just zeroes out in terms of torque anyway. It's like pressing on the door hinges of a door. It's never going to turn the door, right? Right. If you have so that goes away. So only these 2 weights provide any kind of torque relative to that point. And now we've just narrowed it down to the one unknown, which is, well, what is this big guy right here? And you could solve for that, okay? Because you could, bam, know that, boom, 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 right? So yeah, you slide this around until it balances. And once it balances, then you can solve for the unknown, right? That's actually the exact principle that a triple beam balance works. Yeah, speaking of which, triple beam balance, which is, again, kind of this right here anyway. Suppose you took this to the moon. Would this give you the exact same mass reading on the moon as it does on Earth? Yep, because notice the G cancels out, right? G cancels out. Yeah, right? Like you need the same proportional location. Yeah, it would give the exact same reading on the moon. And then, did I get these? Oh, okay, right. So in place of this triangle pivot, I put the spring scale here, but this is kind of mathematically identical. You guys see that? Right. So yeah, so you guys did this version of the lab. And then there was another torque perspective we did that was like the scaffold. You guys remember the scaffold? You guys know that? All right. So, all right, so I got some weight here. If you also included the weight of the beam, you could put it at the at its own center mass, which might possibly be the geometric center if it's uniform. Right, you got that, right? And then maybe have like 2 tensions. Right? You don't know the left tension, the right tension. Right? This now, okay, so that could be the question. What's the left tension? What's the right tension? Right? Now this is another reason that here, if I go back a few posters for 2D equilibrium, just force equilibrium alone cannot solve it. You also need to bring in torque equilibrium. Right? Torque zeroes out, right? Because if it's just force equilibrium, we say, well, I know the sum of these 2 tensions up has to be the sum of the weights down, right? That could satisfy that, right? But how do I know, right? Like if I start sliding this weight around, right? Put it close to the left, close to the right, those 2 individual tensions change. Now they always add up to the same amount, right? But individually they change. So it's not just how much weight, it's also where's that weight located, right? And that's a torque question, right? So I have to pick a point as the pivot point. I've got it covered up, but I'm guessing I picked probably this point as the pivot point. Guys, go ahead on your paper right now, set up a torque equation. Set up a torque equation to answer the question, what is tension on the right side? If I do that, right, that's probably what I got covered up. If I pick the far left point as the pivot point, then tension on the left side provides no torque about that point because it's at that point anyway, right? So that's mathematically why that would be a convenient point to pick as the pivot point, right? So that goes away, right? I got X is the location to the weight, L is the full length of the beam, and L over 2, let's call it the distance to the center mass of the beam. Okay. Set up a torque equation that you could use to solve the tension in the right cable. Right? What's the torque equation? Can you set up a torque equation? Set up a torque equation that could be used to solve what is the tension in the right cable. All right. I think, oh yeah, Addie got it. All right. So, good. This question AP could ask, I mean, I guess any of these that I'm going over in detail could be definitely fair game on the AP, right? So this one, right? So I got two equations. I got the force equilibrium in the top box. Although, like I was saying before, this could be two unknowns if you're trying to chase down. Like if you don't know either of those tensions, that's two unknowns. So you can't solve it by itself, right? But you can solve this whole thing with just torque equilibrium. So here's the sum of the torque goes to 0. Okay, yeah, I did set up exactly like I was. This is what I thought I did, right? So I picked this far left point as the pivot point, and I see that I did that because tension left times 0 distance from that center. This is R cross F, right? Just zeros added in, so that goes away. Boom, that guy's gone, right? Which means I only have one unknown in this one equation, which is tension on the right side. Okay. So we go. Weight of the beam times L over 2. So that's here. Right? Now that's trying to go clockwise. You guys see clockwise? Right? Now, usually clockwise is considered negative. That's why I put the negative sign there. Right? Okay, you guys said. And then what do you got next? The weight of the object is at location X, again, relative to that far left point. So that's why the X. Okay? Again, clockwise, so I also subtracted that. Okay. Then I see this unknown tension on the right side pulling at the full length L, and that's trying to pull it back counterclockwise, hold it in place. So I did plus, right? And I know the torque zeroes out, so equal to 0. Okay. You guys got that set up, right? Yeah, right. If this was a multiple choice question, I could totally see AP offer you this as an option, of course, because that would be the right answer, right? And also, because the question might be like, what setup could solve, blah, 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 right? Just like I asked you. They might also replace this X right here with L minus X and see like how many students can they trip up and say like, ooh, should you play off this distance here, right? Which you could as long as everything was relative to that far right point, right? But you can't switch pivot points, right? So if you pick this far left point as the pivot point, to make sure everything's relative to that pivot point. That's why this is just plain X and not L minus X. Okay. I can see that. See that coming? All right. All right. You guys did the slab version right here. You guys did that. All right. Ooh, okay. Right hand rule. I know AP does not ask about. AP just sticks to clockwise and counterclockwise, right? But this more proper way to do it. If you go to college, you're gonna see right hand rule. So you do R cross F, then your thumb points. It's out of the page. It can be positive torque. It's R cross F. Clockwise into the page, that could be negative torque. Right? But AP just sticks to clockwise, counterclockwise. Okay. AP is going to ask you center mass questions. They probably are not going to have you navigate this formula necessarily, although it could be helpful to know that back in mind. It's like a weighted average. So weighted average of locations. Right? The more massive something is, the more the center mass tends toward that point, like weighted average. That could be helpful. Right? This next slide is a big important slide. Here we go. Here we go. How do we want to cover this up? All right. Just want to ask you guys a bunch of questions about this. Right. Here we go. Here we go. Rotational dynamics. Right, so I got this turntable. This turntable can rotate about this central vertical axis. Right? I got a string wound around the turntable and I'm pulling with some tension force. Boom, 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 boom. You see that? Right. Oh. So write down what is write down the two perspectives for torque. Torque equals what, and torque also equals what. Go ahead and write those down. And then as a third formula, write down angular momentum. Angular momentum equals what? All right, Addie got them. Alec got them. All right, pretty good. All right, so rest of this poster. Right, so here's my two torque formulas in green. Torque equals R cross F. Right, so this radius crossed with this force. Right. Now, conveniently, if a string's round around the turntable, then no matter how you pull a string, it's always going to be at a right angle. Right, so that's nice. Right, this cross product is just right. Sine of 90 degrees is always 1. Right? Torque also equals I times alpha. Okay, that's where, guys, if this turntable is made out of cardboard versus another one's made out of like solid steel, and you apply the same torque to them, they're going to rotate differently. Because that cardboard probably has a little tiny I versus that solid steel probably has a huge rotational inertia. So different angular accelerations, right? Zoom, pull that thing, right? But I bet they could both have the same angular momentum. I've seen AP do that too. If you have a little cardboard turntable versus a thick steel turntable, you apply the same torque to them. They say, which one has a greater angular momentum? Let's see if you guys followed exactly what I just said. Great. All right, you guys ready to show hands? Show hands. Let's see who gets this right. Right. So here we go. I got two turntables. One's made out of little thin cardboard, and the other's made out of solid steel. I'm gonna apply the same torque to both of them. So the same force, the same radial distance. Zoom. They'll stay for the same time for both like a 5-second interval. Right? Right. Which one has the greater angular momentum? The cardboard, the steel, or are they the same? Who says the cardboard has more angular momentum? Nobody says that. Who says the steel has more angular momentum? Who says they're the same? Same. They are the same. Because you know what else I probably could put on this poster? Right? Is angular impulse. Guys, delta L, angular impulse, is equal to what times what? I mean, you could do I times delta omega. That's okay. Right? But I'm thinking, what's the other perspective? Torque times time. Torque times time. Right? You guys know both of those? Both of those? Right? So think about that scenario I just said. Right? Had the cardboard versus the steel. If I applied the same torque for the same time interval, that is the same angular momentum. Right? They would have different kinematic motions because they got different angular accelerations. So I bet that cardboard's like spinning fast, and that steel's like a little slow. Right? But they would have the same angular momentum. Right? It'd be equally difficult to bring them to a stop. Right? You guys got that? Can you guys do this? R cross F is I times alpha. You guys do that too? Right. Angular momentum, I times omega. All right. Ooh. Here, the next one. Right. So the other day, you guys saw a question of a diver dives off a platform, like tucks and goes into a spin and then extends and goes straight to the water. Right. And I think I referenced this poster. Right. So here's the figure skater. Right. Goes into a spin, pulls our arms in, spins faster, and pulls our arms out, spins slower. Right. And the guiding principle is conservation of angular momentum. Right, here's angular momentum is I times omega, and it's conserved for a closed system. Okay, so you guys navigate that. Oh, this next poster, this next one. I got a couple of graphs queued up. Okay. Guys, draw a pair of graphs. Torque versus time and angular momentum versus time. Go ahead, draw those axes. And let's do a scenario for constant torque. Let's do constant torque. I'll change the scenario in a bit. Let's start with just constant torque. What did those two graphs look like? So maybe a story that could attach to that is, I got a string wrapped around a turntable. I'm pulling with a constant force at a constant radial distance. There's your constant torque. Okay. Let's say I pull that for like 10 seconds. Okay. So it's a constant torque for some time interval. What do those two graphs look like? All right, Addy got them. Alec got them. Close. Yeah, what is the unit for angular momentum? Let's check this out. So you guys got these. Okay. So let's think how you could possibly get that. I got kilogram meter squared per second here, right? Okay. So here, you could play off this. Like, if I know L is I times omega, and I remember I, rotational inertia, was like kilogram meter squared. So this is some kilogram meter squared. And omega, that's like radians per second. Now the radians all drop, and I'll just do over seconds. So that'd be kilogram meter squared per second. Boom, that's that unit right there. Okay. Now, if it's angular impulse, there's a different perspective on this you might see, which is torque could be in Newton meters, time is in seconds, so it could be Newton meter seconds. So you could list this as Newton meter seconds to be the equivalent. Right? Yeah, so there's a constant torque, and then the angular momentum would be increasing at a constant rate. And there's the relationship, boom, boom, just like that. Okay, let's do a different scenario, because you might see that. Actually, there's a really good chance you're going to see exactly that. Right? But AP could go a little bit trickier, maybe. Okay, let's do, let's get a next sets of axes here. Let's do a torque versus time, and angular momentum versus time. Okay, let's say for an increasing torque. Actually, I'll give you guys the torque graph. Right. So what if torque versus torque in Newton meters versus time in seconds, right? What if there's an increasing torque, right? Which should be less likely you'll get that, but you could, it could give you that, right? So angular momentum in kilogram meters squared per second, time in seconds, right? What does the angular momentum graph look like? Guess what shape is that going to be? Parabola. It will be. I have seen this come up before in AP. So yeah, they could ask you that. Okay. So you guys navigate that? Okay. It's kind of like, here, let me give you guys an analogy. Okay. Going from torque to angular momentum is, it could be a force to regular momentum. It could be like going from speed to distance, right? Like if your guys constant speed on I-95, just 70 miles an hour, 70 miles an hour, 70 miles an hour, right? But the distance you pick up is changing, but it's changing at a constant rate, changing 70 miles every hour, right? Okay. But what if you got in your car and you slammed on the gas pedal so you were speeding up the entire time? So now you're watching the speedometer and it'll go, right? That could be like that. Now the distance you cover actually would be a parabola, wouldn't it? Right? It's the same type of relationship. See that? All right. This next one, almost for sure, you're going to get a question on this. Right. So let's do angular momentum for a point mass. Right. So here I got. Okay. So I got this point mass coming in. It's gonna bam. It's gonna hit that stick. Right. Notice I have it coming in perpendicular to the stick. I've always seen AP do that, so that's nice. Right. Here's a pivot point at the top. This whole stick's gonna rotate about that pivot point. Maybe this is horizontally oriented, maybe this is vertically oriented. Right. But like right after it, bam, hits. Right. Maybe it sticks, maybe it bounces. A lot of different variations on that. What do I want to ask you guys? Right. Guys, what is the angular momentum associated with that scenario? What's the formula? MVR. There you go. Just take your regular momentum, MV, and multiply by this distance R. Right. Now, actually, one more technicality. It's actually a cross product, kind of like torque was. Right. So if you go to college and they have this coming in at like a 60-degree angle or something weird, then it's actually R cross MV. Right. But I've always seen AP do the perpendicular version, so you can see MVR. Okay. So regular momentum times this radial distance R, boom, boom, put together. Okay. Okay. Now the follow-up question to this could be, how fast does this start swiveling? Right. They might give you some formula setups. They might give you some numerical values and ask you to solve for a number, right? Could you set this equal to I times omega, right? I times omega. If you know the post-collision I, rotational inertia, then you could solve for omega, right? How fast is it rotating? Right. This next one's a little tricky. Curious to see if you guys can get the setup right anyway. Right. Let's say you're spinning a basketball. So start on your finger, just starts from rest, and you bam, you hit it with some force with some time interval, maybe like a fraction of a second, bam. So you apply that force at this radial distance. The basketball has some rotational inertia, okay? And I want to know how fast is it spinning as a result. Okay? Here, write down anything you think you could possibly use to solve that. Hey, a couple months ago, we were saying angular momentum or angular impulse was like torque times time, maybe something like that. You guys remember that? Like I bet if you hit it a few times, that'd be like extending the time interval effectively, right? Like if you hit it once, like bam, first if you hit it like bam, 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 isn't it like 3 times the time you're hitting it? Right? What should make it spin faster is the time has to be a variable, I think, right? Okay, so torque times time should be changing angular momentum. Oh, and angular momentum was I times omega. Ah, wasn't that all true? Right, let's see what exactly am I covering up here? Okay, there you go, there you go. Right, so torque times time is going to result in an angular impulse, right? And that angular impulse is I times omega, right? As long as it starts from rest, that would be true. So it's kind of implied here, starts from rest. See, torque would be R cross F, right? And then, right, okay, now this is a substitution I did that I pulled it off that table. So this is specific to a basketball, this 2/3 mr squared, right? If it was like a foam ball, that might be 2 this, things like that. Okay. There you go. There's how fast it ends up rotating. Hopefully this makes sense too, right? If you apply a greater force, it's going to spin faster. If you apply for a greater time interval, it's going to spin faster. If the ball is more massive, it's going to spin not as fast. If the ball has a larger radius, it's kind of a trade-off, because you might think, well, maybe it's more because you're getting more torque, or maybe it's less because it's more rotational inertia. And overall, it ends up being less because the mr squared beats the RF. Okay, so we have that way. So overall, it's less, right? And then the 3/2 is specific to the basketball. Okay. All right. Ooh, ball rolls down incline. Okay. So I have 2 posters for this. Now this one's the tricky one that goes through torque and okay. Okay, so you can get the linear speed at the bottom, right? I'm not going to necessarily recommend that method, although you can get the right answer. Okay. But this next poster, here we go. This next poster is the same scenario, but it's with conservation of energy. Now this one, I think would be in the realm of maybe a harder question AP could ask. Right? So, how fast is the basketball moving at the bottom? Suppose you have a motion detector at the bottom of that incline. How fast is the basketball going at the bottom of the incline? Just set up the conservation of energy equation. Can you do that? Can you set up the conservation of energy that could eventually solve that question? So all you gotta do is set up the conservation of energy that could eventually solve that question. How fast is the basketball moving at the bottom of the incline? All right, Addie got it. All right, let's take a look here. Okay. So, oh, there it is. That's all I was looking for. Boom, just that. Right. That could be what AP asked you. That could be the multiple choice answer. Boom, right there. Right. All right. Now, if you had to go a few more steps, here's how it finishes out. Right. So, this H you might have to solve in terms of L and theta. Ooh, is that true right there? H is equal to L times sine theta. Right. You guys gotta know that, right? Right. Okay, so maybe right, this H could be L sine theta. What else I got here? I for basketball could be 2/3 mr squared. That's okay. And then this omega could be V over R. Think about that earlier. Put it all together. Solve for V. That's how you do that. right, roll race. So got different rolling objects down this incline. Notice there's a coefficient of friction for all these rolling objects, right? But I have one frictionless lane. Now this air hockey puck's going to beat everything. Ooh, guys, who could tell me how fast is this air hockey puck moving at the bottom of this frictionless lane in terms of this height drop? How fast? Square root 2gh. Right, same as Galileo dropping balls. Right. Now all these other ones are going to going slower than that because some of their energy goes into making it rotate. And they'll finish the race at different times, depending on their rotational inertia. Well, should say rotational inertia, I think, divided by mass. Right? Anyway, it has to do with mass distribution, right? So like a marble and a bowling ball are going to finish side by side because they're both solid spheres, right? But then, right, so they'll finish in this order, right? So the more mass is distributed closer to the outside, the slower it's going to finish. All right, is that? Hey, that's all of them. That's all the posters.